Hello, welcome to Lecture 1 of Electrical Circuits 1. In this lecture, first we're going to provide a brief course overview. The course subject matter is overall about system modeling, analysis, and design. I'm going to spend the first part of this lecture talking about what these things are and introducing you to some of the basics of the philosophy of where we're going to from this point forward for the rest of the semester. After that, I'll introduce some basic circuit parameters. Voltage, current, charge, power. We'll need those throughout the rest of the semester when we're dealing with our circuit analysis. Toward the end of the lecture, we'll introduce the passive sign convention. The passive sign convention is very important. If you don't use it properly before you start your analyses will not make any sense. Luckily, just because it's extremely important doesn't mean that it's difficult. It's really, really easy to do. You just have to make sure that you do it right and you pay attention to it. The related educational module here is section 1.1. There's some suggested information that you should know before starting the class. There's also some suggested additional classes that you might want to be taking at the same time you take this one. So it's suggested that as a prerequisite, before starting this class, you should have at least a basic exposure to electricity and magnetism. In general, that would be presented in a second semester college level physics class. A high school physics class may be appropriate, may give you the information you need if it was a good one. You should also have probably a couple of semesters of calculus under your belt before you start this class. We will be doing integrations in this class. We will be finding maximum and minimum of functions. We'll need some calculus-related tools. I strongly recommend that as a co-requisite to this class, you take a differential equations class. We will be writing and solving differential equations during this class. Okay? If you're taking a differential equations class at the same time, they will give you a lot of theoretical background that will help you understand what we're doing in this class and why we're doing it. Now, if pressed, I will admit that both these sets of requirements are a little bit weak. I've had students make it through the class without having had some or even any of these. However, you need to be extremely motivated if you're going to do that. So when I introduce a topic that requires some prerequisite or co-requisite knowledge, I will explain it briefly at the appropriate point in this class, but I won't get into a lot of background information about it. Our primary goals for this class are to provide an introduction to modeling, analysis, and design of electrical circuits. Now, quite often we will use what is called a systems level approach to the electrical circuit design, analysis, and modeling. That simply means that we will represent our physical device as some kind of system. The system will have some input and some output, denoted by U of t and Y of t. U of t is provided to the system by the outside environment. Y of t is provided by the system back to the outside environment. The system itself can often be considered to be a black box. The modeling aspect of this class is generally to determine the functional relationship between the output Y of t and the input U of t. The system is going to be performing some process on U of t to produce Y of t. That functional relationship consists of the model of the system. In this class, most generally, the functional relationship between Y of t and U of t will be an ordinary differential equation, although for the first part of this class, quite often these functional relationships will be algebraic. Now, one important thing to note is that once we've got this functional relationship, we will often start thinking of the systems in terms of these functional relationships rather than the original physical device. That has its good side and its bad side. Its good side is that it gives you an ability to handle a wide range of systems. We'll be emphasizing electrical circuits, but a lot of the techniques provided in this class are appropriate to mechanical systems, thermal systems, fluidic systems. Okay, the functional relationship is really what's important. The downside of thinking in terms of these functional relationships is that sometimes it's easy to lose track of the fact that this was originally a physical device. There will be limitations on how accurate this mathematical representation is. Okay? If you have forgotten that this was originally a physical device, you have lost the ability to assess whether your mathematical relationship is actually reflecting the physics of what's going on in here. I now want to define what I mean by modeling, analysis, and design. When we model the system, what we are doing is determining the functional relationship between the input and the output that I talked about on the previous slide. We're taking the physical device, we're analyzing that physical device in order to determine the mathematical relationship between the input and the output in general. System analysis means that given this functional relationship and some specific u of t, we determine some y of t. For example, we have some voltage applied to our circuit. We're representing our circuit as some mathematical expression. We may want to determine what the power in some resistor is for that specific input. So we're determining some specific output for some given specific input. System design is maybe the most complex of the three categories, and we'll just get into design a little bit in this class. Design means that what we're doing is creating a system which provides some desired relationship between the input and the output. We know what we want the system to do. Quite often that's represented as some mathematical functional relationship between an input and an output. We want to do what is called realizing that mathematical relationship by creating a physical device that will perform that process. Now I want to provide a graphical representation of what I mean by modeling, analysis, and design and their relationship to the physical world. We really want to firmly fix in our minds that there is a physical entity happening. We are using mathematics to represent that entity to some extent. We have to kind of divorce those two things in order to keep track of both of them. So we have some real world, which consists of a physical system, some electrical circuit in general for us. We will also be representing this physical world mathematically. Now, we're going to always start out with some physical system. For us, this will be an electrical circuit. For a mechanical engineer, it may be a thermal system or some kind of fluidic system. We're going to take this physical system and write some mathematical relationships that we feel govern the physics of what's going on in here. We've now transferred ourselves from the real world into mathematics land. Once we're in mathematics land, we can analyze what we think this physical system will do. So depending on the complexity of this mathematical model, we may do some hand calculations to determine the desired parameters, the specific output that we expect this system to give us. More realistically, for any reasonably complicated system, we'll probably do our analysis using a computer. We'll simulate the response of the system using a computer. Now, we really need to be concerned about whether these analysis results actually match the real world. So in the real world, generally we're going to take this system and test it. Generally under the same conditions that we're doing the analysis for, or we can do the analysis specifically for the conditions that we're testing. Then we'll take the test data and compare that to the analysis results and see whether they agree to a satisfactory level for us. If they don't agree satisfactorily, that means our original mathematical model left out something important about the physics of this system. We may have to go back and revise our mathematical model and redo this analysis section and continue to compare our analyses with the test data. Now, once we've revised our mathematical model so that it reflects reality consistent to what we're testing, we may use the results of these analyses to modify our system or redesign it. So we may try to get some desired response out of this physical system by redesigning parts of the physical system. Now, Leaving this in mathematics land is generally not appropriate for an engineer. We're always wanting to build something that will do something in the real world. So once we've created this design, we'll go back and implement that design, build the actual circuit or system, and test it. Now, at this stage, you also still run the risk that your analysis that created this design may not be reflecting reality accurately enough. Your design may not actually meet the requirements. That may require you to go back and revise your original mathematical model. So one really important thing that I want to get across with this slide is that design especially is a very iterative process. Okay, you end up trying something, maybe it doesn't work out, you may have to go back and revise things and try again. Now, as I mentioned earlier, your model may or may not reflect the physical behavior of the system that you want to reflect. There are actually a number of different approaches towards modeling systems. So regardless of the fact that in this class we will stick with the most simple approaches for system modeling, I'm going to give a quick overview of kind of the broad categories of modeling approaches so that you can sort of see where we stand in the overall world. Okay. A lumped parameters model is appropriate if system parameters change slowly relative to the component response time. Okay, the component, whatever it is, be it electrical, mechanical, thermal, fluidic, has a lot of time to respond to whatever is happening. If you have that condition met, in general, the type of model you will end up with consists of ordinary differential equations. Now, they can be algebraic, but for the most part, I will be emphasizing time-varying stuff, which implies differential equations. Okay, here is an example of a lumped parameter system. It's a simple slinky. Okay, if I hang the slinky from one hand and move my hand up and down very slowly, the bottom of the slinky moves up and down. Now, this looks like a spring with a mass at the bottom of it. At any given time, the spring is either compressing or expanding. All parts of the spring are doing the same thing at any given time. The mass, which consists of several coils of the spring at the bottom, is not really stretching. I can conceptualize this system as the following. I may have some support at the upper end with a spring with spring rate K upon which is hanging a mass M. My input might be the motion of the top of the spring, and my output might be the motion of the mass. Now, this spring I can assume is massless. The mass I may assume has no spring rate. Those are approximations. This spring has mass. Just for the purposes of my model, I'm going to assume that it doesn't. What I'm going to hope is that the mass of the spring is not important. Likewise, I'm going to hope that the relative motion of those little coils at the bottom of the spring is not going to contribute significantly to y of t, and I can assume that this has no spring rate. What I've done is lumped the system parameters. I've lumped all the spring rate at one point. I've lumped all the mass at another point. As long as I don't move this spring very rapidly, that's probably going to be okay. Now, conversely, if parameters are changing rapidly relative to the component response time, we will have to use what is called a distributed parameter system. Not all parts of the component will be responding the same way because the information can't get through the component fast enough. If you're doing a distributed parameters model, in general, your modeling approach will consist of partial differential equations. As you might guess, we'd much rather do this than this. Here's my example of a distributed parameter system. It's the same slinky that I used before. Please notice that although the system hasn't changed, the system may be doing something that requires me to model the system differently because different conditions apply. So now I'm going to take this slinky and stretch it tight. If I change the displacement of one end of this slinky very rapidly just by releasing one coil, what I end up doing is propagating a wave down the slinky. It bounces off my hand at the other end, propagates back. As it goes back and forth, it turns into kind of a jittering motion of the spring. Okay? Not all parts of the spring are moving the same way at the same time. I can't lump the mass and the spring rate because at any given time part of the spring is acting like a mass, part is acting like the spring rate. It has to be distributed throughout the entire system. It's governed by a partial differential equation now. Linear systems are those which have, as the name implies, linear relationships between the dependent variables in the system. These are very nice. They tend to be governed by linear differential equations or, as a special case, linear algebraic equations. The really nice thing about this is linear equations have a unique solution. If you can write these equations and solve them, you will always end up with only one solution. Here's my example linear system. It's still my slinky. If I stretch an ideal spring, Hooke's law tells me that the displacement that I get is proportional to the force that I apply. So if I stretch it to some position, increase the force incrementally, I will increase the displacement incrementally. The force and the displacement will be related by a linear relationship with some constant of proportionality, which is the spring rate. Graphically, that looks like this. If I plot the force versus displacement, where x is displacement and F is force, Hooke's law tells me that F is equal to k times x, where k is the spring rate of the spring. That's a linear relationship. If I plot these two things, I get a straight line. The slope of this line is the spring rate k. So, for a linear system, all the governing relationships between dependent variables have to be linear. If I plot one dependent variable against another, I will end up with a straight line. If the relationships between dependent variables in a system are nonlinear, that is, if I plot two dependent variables against one another and end up with something that is not a straight line, the system itself is said to be nonlinear. If the system is nonlinear, it's still governed by differential equations, but the differential equations themselves are nonlinear. That has a couple of major drawbacks over linear differential equations. First, they're just more difficult to solve, flat out. Second, if you do get them solved, they may actually have more than one solution. More than one solution implies that the system can operate at more than one point. So you may design this system to operate at some point. If it's nonlinear, it may decide to go ahead and operate at some other point, which you may not be very happy about. We'd much rather design linear systems than nonlinear systems. These are tough to deal with. The problem is that any real system is ultimately going to be nonlinear to some extent. What we tend to try to do is take a nonlinear system and approximate it as a linear system, design to that, and hope that everything works out. My slinky can also have a nonlinear behavior. Hooke's law is a good way to model this system if the displacement is small. If, however, I displace this a lot, the more I stretch it, the harder and harder it gets to stretch the spring. In fact, in the extreme, after I stretch this far enough so that it's uncoiled all the coils and it's a straight wire, I would have to plastically deform the wire in order to continue to stretch it anymore. That would require a lot of force just to get a little bit of displacement. Likewise, If I try to compress this spring, once I've compressed it to the point where there is no air gap between the coils, I have to apply a huge amount of force if I want to try to compress this anymore. The metal actually has to deform in order to compress it. If I plot this stuff graphically, this plots the same parameters that I used before, displacement and force. For relatively small displacements or small forces, yeah, Hooke's law is going to hold. The force and the displacement are going to be approximately linearly related. As the displacement gets larger and larger, though, it may cause more and more force to be applied in order to get the same relative displacement, right? In the limit, as this spring entirely uncoils, it takes a lot of force to get a tiny bit of displacement. Likewise, if I compress the spring, once the air gap between the coils is gone, it's going to require a lot of force to get a very small amount of displacement. This is now a nonlinear relationship. Whether we can approximate it as a linear relationship or whether we have to take into account this nonlinearity is a decision that we have to make when we're modeling the system. Finally, there are what are called time-varying systems. In a time-varying system, the physical parameters in the system may vary as a function of time. For example, a light bulb, the resistance of the filament changes as the light bulb heats up. It may appear that the physical parameters of the system are changing with time. If that happens, the system is governed by differential equations with time-varying coefficients. We can also consider our slinky to potentially be a time-varying system. If I'm operating this slinky, okay, bouncing it around, and I decide to change, for example, the temperature on a regular schedule, the physical parameters of this slinky, like the Young's modulus, which contributes to the spring rate of the slinky, those may change as I change the temperature. I'd have to change the temperature quite a lot, granted, but I could make them change. If the temperature is changing as a function of time, it may look like the slinky's parameters are changing as a function of time. The resulting governing equations would now be differential equations with time-varying coefficients. In this class, in Electrical Circuits 1, we will restrict the category of models that we will be creating. We're only going to worry about lumped parameters models of linear time-invariant systems. So the governing equations that we create will be either algebraic equations with constant coefficients or linear differential equations with constant coefficients. We're doing the easiest possible case in this class. There are a few basic electrical parameters that we'll be dealing with throughout the course of the semester. I'd like to introduce those now. The most fundamental electric circuit parameter is charge. It is abbreviated as lowercase q. The units of charge are coulombs, capital C. 1 coulomb is defined as about 6.24 times 10 to the 18th electrons. The fundamental unit of charge is 1 electron. Charge has to occur in integer numbers of electrons. This minus sign is because when these analyses approaches were originally being generated, people did not think in terms of moving electrons around. They were thinking in terms of motion of positive charge. It wasn't until later that they realized that charge motion is done by moving electrons. This negative sign accounts for that difference in outlook. Now, although charge is extremely fundamental to any electrical analysis, we won't be using it directly very often in this class. What we are interested in is not charge, but the motion of charge. We're interested in transferring energy. We want to get energy from one place to another in our electrical circuit in order to perform some useful task. So this parameter won't get used a lot. However, we have a couple of others that will allow us to quantify charge motion. The first of these is current. It's abbreviated as lowercase I. It is the rate of change of charge with time. So I is dq dt in mathematical form. So what we're doing is sitting at some point in our circuit and watching electrons go by us. The rate at which they're going by gives us the current. The units of current are amperes, abbreviated as capital A. Units of charge are coulombs. Units of time are seconds. So amperes are actually coulombs per second in more fundamental units. Our next circuit parameter that's going to be of great direct importance to us in this class is voltage, usually abbreviated as lowercase v. Voltage quantifies the change in energy of a unit charge at two different physical locations. So we're taking a charge, or we're looking at the same charge in two different places, two different points in our circuit. There's going to be a voltage difference that characterizes the difference in energy of those two charges, or that one charge at two different locations. So voltage is dW dq, or a rate of change of energy with change in charge. Units of voltage are V, capital V, volts. Units of energy are joules. Units of charge are coulombs. Volts are joules per coulomb. The final parameter of direct concern to us at the moment is going to be power. Power is, consistent with your physics class, the rate of change of energy with time. So power is dW dt, where W is energy. Now I can use the chain rule to expand this into dW dq times dq dt, and I can think of the dq's as kind of canceling through a multiplicative process. dW dq was previously defined as voltage, dq dt was previously defined as current, so power in the electrical world is voltage times current. The units of power are watts, consistent with what you've used previously to represent power. There are two main categories of electrical circuit elements that we'll be dealing with throughout this class. The first is passive circuit elements. Passive circuit elements are defined by the fact that the total energy over all time that is delivered to the circuit element by the rest of the circuit has to be non-negative. The passive circuit element can either store energy or dissipate energy. It can't create energy. Okay? So you can store energy in a passive circuit element, or you can dissipate energy in a passive circuit element, but you can't create energy. Any energy in that circuit element has to have been provided to the element by the circuit at some point in time. Contrary to this, active circuit elements can actually supply energy to the circuit. That energy is coming from some external source. So from the circuit standpoint, this element is creating energy and providing it to the circuit. A battery, for example, is performing a chemical reaction which is converted to electrical energy. That electrical energy can be provided to an electrical circuit to perform some useful task. As far as the circuit is concerned, that energy was just created by that battery. Now I want to introduce the passive sign convention. This is extremely important. It's very easy, but it's extremely important. If you don't get the passive sign convention right, then none of your analyses will be meaningful. You cannot rely on any of your results. Essentially, in the passive sign convention, we are going to assume the sign of the current relative to the sign of the voltage. So we're going to assume a current direction relative to a voltage polarity. Individually, we can make the current direction any direction we want it to be, but once we've chosen that current direction, we must be consistent with our assumed voltage polarity. Likewise, we could assume a voltage polarity. Once we've done that, though, our current direction must agree with that voltage polarity. The assumption that we must make is that positive current enters the node which is assumed to be at the higher voltage. For example, for this particular circuit element, if I assume this voltage polarity, the plus minus on the voltage gives me the polarity. It indicates that the voltage at this node is assumed to be higher than the voltage at this node. So if I assume this voltage polarity, I have to assume that current is entering the upper voltage node. Now, that's not the only assumption I could make. It would be perfectly legitimate to assume that the voltage at the lower node is higher than the voltage at the upper node. However, if I do that, I must assume that the current is entering the bottom node now. Current has to enter the node which is at the higher voltage. For active circuit elements, we don't need to make any assumptions. The current directions are given for current sources. The voltage polarities are given for voltage sources. So reiterating this, you can assume arbitrarily either the voltage polarity or the current direction. However, once you've chosen one or the other of those, that dictates the assumed direction on the other parameter. The reason that individually they don't matter is that what you're doing is assigning reference directions for these. You have a reference voltage polarity. You have a reference current direction. It tells you what you think the positive direction is. Okay? Your numbers can turn out to be negative. Okay? If you do your analysis, if you get a negative result, that just means that you assume the wrong voltage polarity if your voltage turns out to be negative and you need to swap the polarity. If your current turns out to be a negative number, you simply assume the wrong current direction. These guys are just telling you how to interpret a positive relative to a negative result of any of your analyses. Now I want to do a few examples of assigning the passive sign conventions. The first example, I have a circuit which has a 9-volt source. Notice that the voltage polarity is given on this active circuit element. It also has a current source, which is 0.5 amps. The current direction is given to us there. We don't need to make any sign assumptions on these active elements. What we do need to do is assign our passive sign conventions to the 4 passive elements represented by gray boxes. Now what I've done is given you what I am going to dictate as the positive direction for either voltage or current on each of those. You need to assign the positive value for the other parameter on each of these passive elements. Now the way this is going to work best is if you stop the video at this point, take a shot at doing the problem. After you've tried it yourself, come back, restart the video, watch me do the problem. So go ahead and pause the video and give it a try. Okay, for this circuit element, I've told you that the current, I1, is assumed to be positive going from right to left. That's my assumed direction of positive current. That dictates the voltage polarity for element 1. Current has to be entering the positive voltage node. This has to be my assumed voltage polarity for element 1. In element 2, I've assumed that this lower node is at a higher voltage than the upper node. That dictates the assumption of the direction of assumed positive current for this element. So for element 2, I2 has to be going into the positive voltage node. I2, if it's positive, is going from bottom to top. Element 3, the assumption is that positive voltage is at the upper node. The voltage polarity here is given. That tells me that I need to have positive current for element 3 as going from top to bottom. Element 4, the positive current direction is given as being going from top to bottom. Current has to enter the positive voltage node. That dictates the assumed voltage polarity for element 4. A few hints relative to the passive sign convention. Now, students recognize that this is extremely important to get this right. Sometimes that means that they spend a lot of time trying to get it right in some sense. Just because it's important doesn't necessarily mean that it's difficult. Generally, it's not productive to try to figure out what the correct positive directions are before you start analyzing the circuit. Just blindly assign assumed voltage polarities and current directions before you start analyzing. Then go ahead and analyze the circuit Negative values will tell you that you just assumed the wrong direction. Don't try to pick the correct direction before you do the analysis. The analysis has to tell you what the correct direction is. So, when you're approaching a problem, arbitrarily choose either the voltage polarity or the current direction for each passive circuit element. I don't care which one you choose. Pick one of them. Then, label the other parameter for each one of those circuit elements so that they agree with the passive sign convention. Okay? Later on, when we talk about doing analysis methods, you will do your analysis using those assumed signs. If you end up with a negative value, it's no big deal. It just means that your original assumption was incorrect. Here's another example. I want to assign reference voltage polarities and current directions for each of the passive circuit elements in this circuit. I have a 2 amp source. Its current direction is positive downward. Now, in this particular example, I haven't given you either the voltage polarity or the current direction. You're going to have to determine both of them. So please give that a try before you come back and watch me do the problem. Okay. Now I can assume either the current direction or the voltage polarity arbitrarily for each of these elements. So for this element, let's call it element 1, I'm going to assume that the voltage polarity is positive at this node relative to this node. That assumption individually doesn't matter. However, once I've made that assumption, I have to assume that I1 is going positive into this node. Now, if you'd made an alternate assumption, I'm perfectly happy if you assumed that the voltage is positive at this lower node relative to the upper node. That's fine. Now, just make sure that you assume that I1 is going into the positive voltage node. For this element, let's assume that it's element 2 and that I2 is positive in this direction. Once I've assumed a positive current direction, that tells me what the voltage polarity assumed direction is. The positive voltage must be at the node which the current is entering. Element 3, say I assume that voltage is positive at the upper node relative to the lower node. That then tells me that I have to assume that I3 is positive downward. Positive current enters the positive voltage node. Again, that assumption is not unique. For example, say I wanted to assume that the positive current in element 3 is I3 positive going upwards. That's fine, as long as you assume that the polarity of the voltage is such that the voltage at the lower node is higher than at the upper node. Then later, when I analyze this circuit, I just know how to interpret positive versus negative results. If V3 turns out to be a negative number, it just means that the voltage is higher at the upper node than it is at the lower node. So do another example of the same thing. In this particular circuit, I have a slightly different configuration of 3 passive circuit elements, and I have now a voltage source of 3 volts with a given polarity rather than the current source that I had before. Please notice that the source that I give you doesn't affect your choice of the passive sign convention. I don't need to use this information to try to decide which direction are positive voltages and which directions are positive currents. I choose them arbitrarily for each individual passive circuit element. So, for circuit element 1, I can assume either a voltage polarity or a current direction. Let's assume that the current I1 is positive from left to right. That means the voltage V1 has to be assumed to be higher at the leftmost node than it is at the right. If I assume for element 2 that the voltage polarity V2 is such that the higher voltage is at the upper node, that's fine as long as you assume that the current I2 is entering the positive voltage node. Element 3, I can assume either the voltage polarity or the current direction. Let's assume that the current is going from the bottom to the top. I3 is going upwards, positive. That means that V3, its assumed higher voltage has to be at the lower node. Okay, the assumption of the current directions and the voltage polarities of this element aren't affected by my other assumptions. I pick them each independently. As long as they agree for each passive element, I'm in good shape when I do my analysis. Okay, one more example relative to the passive sign convention. I have this particular circuit here. It has two passive circuit elements and a 4-volt voltage source. I'm going to claim that I have picked my passive sign convention for each of these two elements in this way. I'm assuming that V1 is higher at this node than it is at this node, and I1 is going positive right to left. So I1 is entering the positive voltage node of this element. Second element, I've assumed that V2 is higher at this node than it is at this node. Thus, I need to assume that I2 is positive into the positive voltage node. Now, I'm going to claim that I've secretly gone off and done some analysis. After I've analyzed the circuit, I determined that I1 turns out to be negative 3 milliamps, I2 is positive 3 milliamps, V1 is a negative 1.5 volts, and V2 is 2.5 volts, positive. I want you to redraw the circuit showing the voltages and currents and their actual directions rather than their assumed directions. So give that a shot, come back, watch me do it. Okay, my voltage source hasn't changed, and I still have two passive circuit elements in this configuration. V1 is assumed to be positive here relative to here. V1 is negative 1.5 volts. That simply means that the actual voltage polarity is the opposite of the assumed voltage polarity, so that V1 1.5 volts is a higher voltage at the left node than it is at the right node, the opposite of what I assumed. I1 is also negative. That means that this current is also in the opposite direction to what I assumed. So I1 is actually in this direction, and it is positive 3 milliamps in that direction. For element 2, I2 is a positive 3 milliamps. That means that this direction is correct. So we have 3 milliamps positive. Likewise, voltage V2 is a positive number. So this is the actual correct voltage polarity. I don't need to change that. That concludes lecture 1. Next time, in lecture 2, we'll come back and we'll briefly review the passive sign convention. We really need to make sure that that's done right before we try to do anything else. Also in lecture 2, we'll start talking about power generation and power absorption. Those two concepts, whether an element is absorbing or generating power, will hinge very heavily upon understanding the passive sign convention. After we do that, we'll start talking about a particular type of circuit element, resistors, and the voltage-current relationships for resistors, which is called Ohm's law.